I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
Space. Time.
brain,
Life. The universe.
Hello and welcome to The Naked Scientists, where this week we're answering your science questions, including:
is the Earth's core cooling down?
how do messages from space probes get back to Earth?
And why sleeping on your front might increase your risk of getting Alzheimer's disease.
I'm Kat Arney.
And I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
So let's begin by meeting the team. And we have with us today neuroscientist Laura Ford from Cambridge University, Andrew Norton, he's an astrophysicist from the Open University, Marianne Holness is a volcanologist, geologist and all-round rocker from Cambridge, and finally Chris Smith, who can answer pretty much any question, and I will handle anything genetics-y.
Well, let's jump straight in then. This one, I think, probably is for you, Marianne.
how do toads predict earthquakes?
And that was sent in by Paul. What do you think?
You know, at first sight, it sounds like a really crazy question. But in fact, it's a subject of a really serious research effort, particularly in China and Japan, because everyone is very, very anxious to know when the next earthquake is going to go off. And so people are exploring all avenues. And in fact, you know, a very, very long time ago, 373 BC, there's the first report of strange animal behaviour immediately preceding an earthquake. This is an earthquake that wiped out a really important Greek city of Helika. Apparently 5 days before the earthquake, rats, weasels, centipedes and snakes all left the area and ran away. And so ever since then, people have thought that animals know much more than we do about whether earthquakes are on their way. The question is, how on earth do they do it? Now, there's a very obvious way of doing it for animals, that particularly those that live in burrows, and that's because when earthquakes go off, they send off two types of waves. There's P waves, which are like sound waves, and there's S waves, which are more like light waves. And the P waves come much, much faster than the S waves. And if you're the sort of animal like gerbils, for example, that communicate by thumping, you're really, really tuned to vibrations. So you can hear these things coming before humans can, and that's when you leave your burrow, because otherwise it'll collapse in on you.
You're sort of suggesting then that the animals are picking up on either the earthquake itself or maybe some of the rumbles that presage or predate an earthquake, because earthquakes sometimes give away sort of signature rumbles before they actually move, don't they?
Yeah, they'll be picking up on pre-shocks, but any earthquake will send out these two sorts of waves, one of which comes much faster than the other, and they'll pick up these fast ones. Earthquakes are caused by the movement of faults, and faults are generally all sort of jammed up and they're accumulating strain, and then suddenly the strain will be too great and they'll go on a sort of pop open. But as they start to slide, it's going to affect the water table. So you get water movements changing, you'll get springs stopping flowing or starting flowing. So the toads might have been picking up on something to do with water, with humidity in the soil, something like that. But, you know, picking up something 5 days before, now that's a real mystery.
So there are lots of potential environmental cues that they could be picking up on. Thank you, Marianne.
I think that's totally fascinating. Andrew, here's a query for you. We've got a question from our listener Arun asking how signals sent from space probes get back to Earth. Juno is about to reach Jupiter. We had loads of those amazing pictures coming back from the New Horizons mission that's out by Pluto. How are they getting back to us?
Well, the simple answer is it's just a radio wave. It's a radio transmitter on the spacecraft that sends a signal to Earth.
So it's basically like a Snapchat.
Kind of. The thing is...
Instagram.
If only it were that simple. The thing is that the transmitters on these space probes, they're so low power. You know, the power requirements of the spacecraft are just a few watts, so that the transmitter is only beaming a tiny, tiny, weak signal back to us. And so it's literally sending the data back a bit at a time. So, you know, you don't get a whole picture at once. You get each pixel one by one. And so you have to build up the pictures over time. And that's why it takes so long for the data to get back, particularly from that New Horizons probe out at Pluto.
Sounds like my home internet connection. Pekka Oilinki has tweeted at Naked Scientist and says, what kind of camera can take photos of Pluto where light's very limited? He wants to know sort of things like the sensor, the ISO rating, the shutter time, the F value, if you know it.
Yeah, I'm afraid I don't know the details like that, but it is literally a digital camera. That's what it is on board these spacecraft, taking pictures in low light levels, perhaps in the infrared rather than visible light. But yeah, it's working just like the camera on your phone, but working in those low light levels.
It is incredible to think that those amazing pictures that we saw of Pluto, the sort of the heart shape on its surface, 1 pixel at a time over thousands and thousands of miles.
I know, it really is incredible. And, we tend to think, it's just a space probe out there in the solar system sending back the pictures. But yeah, it's taken years to get there. And even the signals themselves will take, hours to get back to Earth.
It's 6 billion kilometres to Pluto. Light goes about 1 billion kilometres an hour, so it's 6 hours for the message to come back. Marion?
So how long is it going to take for all the data to eventually get back to us?
Well, I guess, they'll keep going till the power runs out, really. It could be many, many months yet.
So in many ways, it is like a mobile phone. You just keep taking those photos, keep posting them on Instagram until your phone dies.
Exactly.
Thank you, Andrew. Kat, here's one for you. It's on genetics.
Okay.
Jan, or Jan, not sure which of the two, would like to know what determines whether a gene is recessive or dominant, and what do those two terms mean?
So this is a really great question, because quite often when we learn about genetics in school, we learn about the idea that there are dominant genes and there are recessive genes. But actually, in real life, it's very, very complicated. And lots of us learn about genetics through things like Mendel's pea plants. So you have red flowers or purple flowers and white flowers. And if you cross a red plant with a white plant, you tend to get red plants because the red gene is dominant. And that's because the red version of the pigment gene is making a pigment. It's the red pigment that colours the flowers. And the white version of the gene is actually broken. It's not making any pigment. So as soon as you have a working gene that makes pigment, the red one, it will be dominant.
So it's like a blank canvas. The white one gives you a blank canvas. The red is flicking paint at the canvas.
Exactly. So usually like a recessive gene or a recessive version of a gene is one that's not working or not working properly or not working very well. But actually, I've been doing a lot of research lately, talking to a lot of geneticists, and it's a very oversimplified concept, this idea of dominant and recessive. And you can see it when you look at things like hair colour or eye colour in your family. You might think, this colour should be dominant over that, but it's a bit more complicated than that. So yes, there are some traits where if you're making, if a gene is active and making something like a pigment or a molecule, or even making a faulty and overactive molecule, then that will be dominant. And if something's recessive, then it is not making something very well. But yeah, actually, there's lots and lots of genes contributing to lots of traits, things like height, intelligence, even many, many diseases. So the idea of something being very simply dominant or very simply recessive is not a helpful idea for many, many traits and diseases.
The definition I saw when I had my first genetics textbook was that a recessive gene is one which is clinically manifest only in the homozygous state. Let's put that into plain English. You need to have 2 copies of that gene present in order to see its effect, because if there's another gene there that isn't recessive, it will sort of trump the genetic one and you'll see the manifestation of that gene.
Exactly. Usually a recessive gene is something that's not working properly. So a great example is cystic fibrosis. If someone inherits 2 faulty copies of a gene called CFTR, then it means they don't make this molecule that shuttles salt in and out of their cells, in their lungs, in their guts, and so they have all these problems. But actually what's really interesting is that now we're starting to look at more and more people's genomes, do more and more genetic sequencing. We're discovering that lots of people are walking around with 2 copies of broken genes, for want of a better word, but they're okay. So really, this concept of dominant and recessive, I think we need to really rethink it the more we discover about our genomes. Right, well, that's my bit. So now it's your turn, Chris, because we have this question from Helen.
My mother-in-law has quite a few fatty lumps all over her body. She has had 10 previously removed and they just seem to reappear. They are not painful in any way, but they are quite large. Why do they form?
It sounds to me like these are what we call a lipoma, or when you have more than one lipoma, they are lipomata, which are benign tumours or benign growths of fat. They may also be fibromas because that's fibrous tissue, but they sound like the fatty equivalent, lipomas. There is a condition, and it's called familial lipomatosis. It's very rare. About 0.002% of people have this. It's caused by a gene, which is usually a dominant gene, as you've just heard what that is from Kat. And that means you usually see this running in families. But because with every generation you pass on 30 to 50 new genetic changes or mutations from parents to offspring, these changes can arise sometimes de novo, in other words, out of the blue. And so there may be no obvious family connection because this is a new mutation. We don't know why it happens, but we know it's twice as common in men as women. It tends to occur on the trunk or on the limbs. It tends to spare the shoulders and the head. It is not harmful, really, and most of the time these things, despite being a bit unsightly, won't do you harm. They can be shelled out or removed, but because they are growing from a preponderance of the fat cells to form these little benign tumours or growths, they do recur. And so just because you take one out, you may get another one somewhere else.
This is The Naked Scientists with me, Kat Arney.
And also with me, Chris Smith. And it's Q&A time this week. So if you would like us to answer your science questions from why the sky's blue to why we have dreams, then ping us an email. It's chris@thenakedscientist.com, and we will do our best to include them in our next Q&A show.
So let's have a question for you, Laura. Perhaps you could tell me and our listener, Qian Cheng, what happens to your brain when you're sleepy?
The way that we look at this is we actually do sleep deprivation studies. So that's exactly what it sounds like. We ask people to come in and volunteer to just be deprived from sleep for a couple of days because neuroscientists like to do that to people.
Why would you do that? That sounds awful.
I know.
Loads of parents who'd sign up for that.
Exactly. They can be our great case studies. So the idea is that we invite you to come in. So this is why parents wouldn't qualify, because they need to be well rested when they start. Because
that rules me out then.
Yeah. We need a good baseline. So we'll invite you in to come for a baseline, and you would undertake a task. So that might be something like a serial addition or subtraction task, which involves our arithmetic, it involves our planning, our working memory. So all of these things that are quite challenging and cognitively challenging. And what we'll do is we'll put them into a brain imager at the same time. And then we'll have a comparison. So we'll deprive them of sleep for 1, 2, or maybe up to 3 days, depending upon the ethics that they get. And we'll have a look at how things change. So how does their performance change cognitively? What's the decline, and what does this seem to correlate with it when we think about what's going on in the brain? And basically they work on metabolic principles. So it's the idea of whatever neurons are active at the time, they need a certain amount of oxygen. These imaging techniques take a look inside the brain and takes advantage of the fact that there are different magnetic properties of oxygenated to deoxygenated blood. So while the blood sends all of this blood, the brain sends blood to the area, the neurons that are being used, and you can see the oxygen that's being kind of taken up by them as a proxy for their activity.
About what is going on when you're feeling really sleepy.
So looking at these two things, basically what we see, they're quite congruent with each other. We have global deactivation of the brain, but there are certain areas that are really hard hit. And those are...
So these are bits of the brain that are just going, just winding down.
Absolutely. And it seems to be dose dependent. So as the days goes on, the decline becomes more progressive. But the areas that are worst hit are the frontal areas and the thalamus. And this really makes sense when we think about our profile earlier, because the frontal lobe is responsible for planning, our executive function, our memory. And the thalamus is what it sits on top of the brainstem, and it's really important for alerting. And it has all of these feed forward and feedback mechanisms with the frontal lobe. So they talk to each other a lot, and it's incredibly important in attention. And one more interesting thing is this idea of when we look at sleep, so when you're in REM sleep or deep wave sleep, they're the first areas to turn off. So it tells us that they are very expensive in terms of their oxygen and their glucose use, and they seem to be what benefits the most from sleeping.
So basically people will make worse decisions when they're tired because these important bits of the brain in decision making are just knackered.
Absolutely. It's the case, and you just have less resources to be able to use, and your brain is not functioning, it's not using energy in the correct way, it's not using its oxygen sufficiently, so you are less able to make a good decision.
Good idea to get a good night's sleep, I reckon.
Yeah. Best prescription for a good night's sleep I've heard. Thank you, Laura. Now, Dave is on the line. He's actually calling from the Shetland Islands. Hello, Dave.
Hello, Chris. Well, first of all, can I just say that I think your programme is absolutely fantastic. And to say, my question is, if dark matter, oblique energy, makes up 95% of the known universe, how can we be 100% sure the Big Bang created it? Could it have pre-existed the Big Bang?
This sounds like one for you, Andrew Norton, who's an astrophysicist from the Open University. What do you think?
Well, yeah, dark energy, dark matter, these are names that we give to things that we really have no idea what they are. We see the evidence for it in the way that galaxies rotate, in the way that galaxies move through space. There must be some other matter there that's controlling how things move through the effect of its gravity, but we have no idea what it is. Dark energy, on the other hand, it's not anything to do with dark matter. It just happens to have a word in common. But that seems to be some stuff, again, we don't know what it is, that is causing the expansion of the universe to accelerate. Now, the simple answer of where they came from is to say, well, if the universe began in a Big Bang about 14 billion years ago, the dark matter, whatever it is, and the dark energy, whatever it is, were created there along with time and space and everything else. Now, that's an easy answer perhaps, but it's not a very satisfactory one. There is another theory. Now, I'm not saying that everybody believes this by any means, but it's an intriguing theory. It's called the ekpyrotic universe theory. I think it's from a Greek word meaning born out of fire. So we're familiar with 4 dimensions, 3 dimensions of space, up, down, left, right, backwards, forwards, and 1 dimension of time. 4 dimensions we're familiar with. That's fine. In the ekpyrotic universe theory, the universe has 11 dimensions. Okay, bear with me. 6 of these dimensions are curled up too small. We can't see them. Let's forget those. But there's another dimension, a 5th dimension, which is a dimension of space that we can't experience. Okay, and the idea is our universe sits on what's called a brane. This is not a B-R-A-I-N brain.
It's Laura was getting all excited
then.
No.
Sorry, Laura. No, this is a B-R-A-N-E brain, a 4-dimensional brain. Membrane, yeah. We think of 2-dimensional membranes like the skin of a drum. Well, a 4-dimensional brain. Our universe, then, in this theory, sits on a 4-dimensional brain. And there's another 4-dimensional brain separated from us across this invisible 5th dimension, this hidden brain. And what we think of as the Big Bang was not a creation of time and space. It was actually a big clap when these 2 brains last came together. And ever since then, the 2 brains have been stretching apart. And the tension between those brains is what we see today as dark energy. And also the matter on that other brain, on the hidden brain, that is the dark matter that's influencing our universe. And the idea is that as these 2 brains stretch further and further apart, eventually, sometime in the future, the 2 brains will spring together, make another big clap, and the whole thing will start all over again.
Effectively, then, gravity can propagate between, or the influences of gravity can propagate between these brains, but other stuff can't.
Yeah.
So we see the effects of gravity, but not other stuff.
Yeah. So the leakage of the gravity from this matter on the other brain is what we maybe is what the dark matter is. Now, I say ekpyrotic universe theory. Not everyone believes it by any means, but I think it's a good fun theory.
Well, I've learned a new word this evening already: ekpyrotic universe theory. David, does that assuage your hunger?
Well, I'm just wondering if this new theory, is this based off string theory?
It is very closely linked to string theory. You're absolutely right. Yeah, as you probably know, the idea of string theory is again tied up with these multi-dimensional objects, these brains. So it's an attempt in a way to link the cosmology to the string theory. And who knows, it could be right. Andrew,
thank you very much. And David, brilliant question. Thank you very much too, Kat.
I find that stuff completely brain-bending. It really does. I'll just stick with biology, I think. So actually, back on Earth, we have a question from our listener, Jan, who wants to know the answer to this one.
I believe the Earth has a solid core made of nickel and iron at a temperature of several thousand degrees Celsius. Correct me if I'm wrong. Why does the core keep its temperature? Why did the core not cool down over the last 3 to 4 billion years or so?
So, Marion, you are our Earth expert. What's going on here? Why does the core keep its temperature, or does it?
It doesn't. It is actually cooling down, and it has been all the way through Earth history. It's been doing it very slowly because it's in the centre of the Earth, and all that heat has got to get out through thousands of kilometres of solid rock. What's interesting is that because it's cooling down, it started out all liquid, so a great big glob of liquid iron and nickel, as Jan says. And as it cooled down, it started to solidify. So in the centre of the Earth now, we have an inner core, which is about 1,000 kilometres in diameter, which is solid. And then the outer core is liquid. And it's the movement of this outer core, in fact, that makes the Earth's magnetic field. But what we can do is use the fact that it's solidifying to work out how hot it is. Because what we can do is we know how big the core is because we can listen to earthquakes and find out where all these different divisions of the Earth are. And the division between the solid and the liquid core is about 5,000 kilometres below the surface of the Earth. So we can work out how much pressure there is there, and then we do some experiments and say, when does iron solidify at these sorts of pressures? And the answer is 6,000 degrees Celsius.
Andrew?
I was just wondering, does radioactive decay in the Earth contribute to that heating? Does that put some heat back in, if you like, as well?
Yes, it does. The Earth started out hot because of all the potential energy that was released when you made the planet in the first place.
That's everything just like slamming
That's everything
together.
slamming together, yes, under gravity. But it's actually cooling much slower than you'd expect if it just had that original heat. Because it's, as Andrew says, we're generating heat radiogenically by the decay of isotopes like uranium, thorium, lead, potassium, some early isotopes, some tungsten isotopes that are now completely dead, so there's nothing left of them. But in the core, you don't really have that. You don't really have radiogenic heat generation in the core. It's all in the outer mantle, the rocky bit.
Absolutely fascinating. Thank you.
Kat, here is one for you from Toya, who says, can we genetically modify plants in order to absorb more CO2? I presume they're going for the point that we're worried about CO2 levels in the atmosphere.
Yeah, kind of plant-based carbon scrubbing. I think in theory, and it's important to think about how do plants use CO2. So they use carbon dioxide in a process called photosynthesis, which is basically sticking together carbon dioxide and water to make sugars. And it's kind of the reverse of what we do when we make energy by eating sugar and turning it into carbon dioxide and water. So they do this through a whole series of enzymes. These are kind of chemical catalysts that do all these different processes, that take the carbon dioxide, they take the water, they kind of stick it together, use the energy from light to do that kind of chemical reaction. So in theory, I think that you could probably make some tweaks to those enzymes to make them more efficient, make them run in slightly different ways. I also think that there are other things that would probably speed up that reaction. Things like heat tends to speed up biological processes to a certain point. After that point, you tend to damage the enzymes. So I think if you could make those enzymes in some way run more efficiently at the temperatures that plants normally grow at, or put the entire world in a greenhouse, which we're kind of doing, that might work.
Thank you very much, Kat.
You're listening to The Naked Scientists with me, Kat Arney.
And with me, Chris Smith.
Today we have a panel of experts to decipher your questions, including astronomer Andrew Norton, geologist Marian Holness and neuroscientist Laura Ford. If you'd like to have your questions answered on a future programme, just drop them in an email to chris@thenakedscientist.com. Chris, can you just answer this one quickly? Steve wants to know, how does a tattoo work?
When you do tattooing, you're putting in big molecules of a dye or ink. It goes in under the top layer of the skin because the surface layers of the skin are continuously being replaced. You have very high cell turnover in the skin. Your stem cells that make skin slowly grow upwards through the skin, and it takes about a month from the time the stem cell produces a new skin cell for that skin cell to work its way up to the top, then get worn off, fall off, and it's replaced by one from below. The tattoo is going in just into that layer. The ink is being taken up by cells in the skin, probably macrophages and long-lived cells, which eat the dye molecules, and it stains the cells, and as a result you end up with that pigment sitting there. But that's why tattoos blur as you get older, because slowly the dye gets carted off to your lymph nodes. It also breaks apart and spreads out a bit more as some of those longer-lived cells die. But you're basically staining the skin. I've got another good one here. Phil Abrahams has emailed chris@nakedscientist.com. When I look at a bright sky, why do I see what looks like thousands of glowing worms crawling everywhere? I think he's seeing. I think this is Shearer's phenomenon. It's the blue entoptic phenomenon. When you look at a bright blue sky, you are seeing the white blood cells crawling through your capillaries on the back of your eye. And the white cells, actually, because of the blue dominance of the light, they actually reflect the white light back at you. And as a result, you see the incidental migration of a cell through the network of capillaries, and that's why it looks like a worm crawling, because the white cells are few and far between in number compared with the red cells, which soak up the light, and you are adapted to the red light, so you don't see them. So I think that's the reason. You should be
careful staring into bright skies. Like, don't stare at the sun, people. That's really bad.
Question from Pekka for you, Andrew. A quick one here. At Naked Scientist, if you'd like to tweet one in. We have observed 2 sets of gravitational waves so far in these experiments that have been announced to a huge wave of publicity. Does this mean, he says, that our universe is full of black holes?
Well, pretty much, yeah. We always suspected that was the case, and we've seen sort of indirect evidence for those black holes out there. We think there's a supermassive black hole in the centre of pretty much every galaxy. But the fact that there are these binary black holes out there, dead remnants of stars that are orbiting around each other, gradually spiralling together and then colliding to give us this gravitational wave signature, they must be going on all the time. And now that we've got the sensitivity to detect them, we're going to be picking them up all the time, I'm pretty sure.
Right, well, moving from, again, outer space into the inner space. Laura, here's one for you as a neuroscientist. Can you help with Shepard's question?
How can I improve my short-term memory?
If you imagine yourself at a party and you're listening to someone and they've just introduced themselves, and
Cats
you think,
at a party? That doesn't.
I'm interested in this because I have like goldfish memory span for people's names. You can introduce me to someone and like literally it's just gone.
So the idea is often we're thinking about what do we want to say next, how important this person might be, or even where's our drink or whatever it might be. And actually we didn't attend to it in the first place. And if we look at theories of attention, it does say that we can shallowly process things that are outside of our main focus, but it's much less likely to get into the very competitive working memory store so that we can recall it. So the first thing I would say is listen, which sounds very simplistic, but it's definitely important. In terms of, there's 2 ways I want to go about thinking about this now. One of them is what we're doing in the neuroscience world, and that's there's lots of things around working memory training.
So is this things like, if I meet someone called Bob, I need to go, hi Bob, how's things with you, Bob? Or just say to myself like, Bob, 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 Bob.
So actually this is the second part, which is actually the strategies that will help you really, and they can be 2 different things. And so repetition is absolutely one in terms of, and many say, and what you're doing is you're kind of embedding it into your pre-existing representations of a memory. So you're actually using your long-term memory stores to enable that process. And that's really what mnemonics works on, which is incredibly fascinating. But we've all done it, and actually I can just whistle-stop tour some things that will help you in that scenario specifically.
Yeah. How do I remember people's names?
How do you remember people's names? Okay, so the first thing you can do is multi-sensory integration. So think about where that person is, what kind of aftershave they might have on. You've got a picture of the visual scene. And what we know is that the more that we're tacking into, the more likely it is to have a long-lasting representation. You've also got very fun pictures that you can make where, for example, if that person's name is Annabelle, you can imagine a really outrageous, huge bell with Anne on the front and Nat on the back. And it can be making a really loud noise. And the more crazy that you make it, the more likely you're able to recall that piece of information. And it's very quick. It's one image and you've picked up the whole scene, and you can even put it in any place that you'd like. So that's very interesting. And if in doubt, you can always use a notepad.
That's what I tend to do. So loads and loads of tips there. So hopefully our listener Shepard will, next time they're at a party or need any kind of memory like that, write it down and make outrageous pictures. Thanks very much for those tips.
Andrew, it says here, I've got to read this out, it's so funny. It says, Andrew, wrap your rockets around this question from 4th grade teacher Lynn.
I'm teaching a bit of physics in my grade 4 class. We were having a lesson on heat transfer, and when I was explaining radiation, I gave the example of the sun. Even though it being so far away, the heat travels a long way and can still warm us. Another example was being warmed from a campfire. Then a young girl asked, well, why is space cold then? As we move closer to the fire, we get warmer. The space between us and the fire is always hot, and we can feel it all the time. Why isn't it like that in space?
Andrew?
Well, the thing you've got to remember is the space between you and the fire is filled with air, and that air gets heated up. The air molecules, the oxygen, the nitrogen, are moving around rapidly. That rapid movement is what we mean by temperature. Things that are hotter, the atoms and molecules move around quicker. Now, in space, it's pretty empty. There's a few molecules, maybe, 1 atom per cubic meter or whatever it is. So there's nothing there really to absorb that energy, that radiant energy from the sun. So that's why space itself is pretty cold. If you had an astronaut in space, they would be absorbing that heat radiation from the sun. So the side of the astronaut facing the sun would indeed get very, very hot. The side facing away from the sun would be freezing cold. So you need something there to absorb the heat, absorb the radiation, to feel the effective temperature.
That is a great question, though. I feel so
really
proud
is.
that school kids are thinking like that. That's really, really scientist in the making. So we've got a question for you here, Chris. So Daria wants to know, what's the best position to sleep in? She says she's heard that lying on your left side isn't good because that's the heart. Is this true? I mean, I can't sleep on my back or my tummy. I just can't. I have to sleep on one side or the other. So, yeah, am I doing a bad thing?
Depends who you are talking about, because if you're talking about little babies, then there's one rule for them, which is there's been a very successful campaign in recent years called Back to Sleep, because very many studies have now shown beyond doubt that the risk of things like sudden infant death syndrome, which is otherwise known as cot death, terrible situation, that risk is lower in babies that are put to sleep on their backs. Once they get older and they can turn over and do all that kind of thing, it's different. But for very young babies, putting them on their back definitely is the best position to sleep in. It's associated with fewer bad outcomes. What about if you're pregnant and expecting a baby? Well, because you end up with this very large mass, especially towards the end of pregnancy, I fortunately haven't had to put up with this, but my poor wife has. You end up feeling a bit like an HGV driver in what she dubbed the I just want it out phase now. It's a very big abdominal pressure, and big blood vessels have to run through your abdomen to carry blood from your legs and the lower part of your body back up towards your heart. The main blood vessel, the vena cava, runs on the right-hand side. Therefore, if you lie on your back, a lot of that mass in your abdomen is going to push backwards and squeeze down on your vena cava, and that's going to reduce the flow of blood back to your heart, which means that your legs are more likely to swell. It means your cardiac output's lower. So you advise, if you're pregnant, sleep on your left-hand side, because that transfers some of the load away from where the big blood vessels are, meaning the blood can get back to your heart more easily.
But
now,
what if I'm not pregnant and not a tiny baby?
Yeah. So for your average punter, there have been a number of studies looking at this, actually. It depends whether or not you want to have vivid, weird dreams.
Oh, I get those anyway. I think it's the scotch.
It could be, or the cheese. There's a study that was done about 10 years ago where they actually it was a small group of people, 63 odd people, and they asked them, what were your dreams all about? And they looked at how they slept, and what they found is that the people who slept on their backs had the most soothing night's sleep. The people who slept on their right-hand side tended to have the nicest dreams. The people who slept on their left-hand side tended to have the most nightmares. It was 40% versus 14%, but very small study. That said, a big study from China with thousands of people in it seemed to corroborate the effect. But then there's the question of, well, what is best for your health long term? And there was a very good study in the Journal of Neuroscience last year. It was by Helene Benveniste, and she's a researcher at Stony Brook University in America. They were asking, well, what happens if we actually look at how the brain responds when you're asleep, and what's the role of sleep? When you go to sleep, your brain cleans itself out. You have an entity called the blood-brain barrier that cocoons your brain away from your blood, and it keeps the brain isolated chemically from the rest of your body during your waking hours. But what that means is that over the course of the day, lots of metabolites and rubbish builds up in the brain, which contributes to you feeling sleepy. So when you go to sleep, actually a system called the glymphatic system kicks in, and it flushes this stuff out of your brain, and that's why you feel refreshed after a good night's sleep.
You've had a good brainwashing.
Exactly. But the question is, in what position is that most effective? Now, we don't know in humans. They did their study in rats. Now, a rat that was on its front actually pooled some of their tracer molecules and showed the least good washout of these metabolites. Rats on their back, they had sort of intermediate levels of washout. The best position was on your side. This is done in rats, so you've got to be cautious. It's a rodent study, but it does appear to hold weight because rats have very similar brain anatomy to us, really. So it looks like to reduce your risk of build-up of muck in your brain, and that muck includes the muck that can cause Alzheimer's disease, sleep on your side. That's the argument. Marion?
But weren't you saying if you sleep on your left, you have nightmares? So you're nicely brainwashed.
Yes, you're nicely brainwashed. We're having nightmares. That's right. But remember, it was a small study, and only 40% of the people had some disturbing dreams. The people who slept on their front in the Chinese study, they dreamt about UFOs and other bizarre stuff. So it could get even worse.
That's amazing. And of course, if you sleep on your back and you snore, you will just be poked all night. Shut up. So a lesson for us all.
Marion, I've got one here for you from Amanda.
I heard recently that there may be cryovolcanoes on Pluto. This was explained to me as ice volcanoes, where instead of magma, molten rock, there is water. But what is the difference between ice and rock? Ice is frozen water, rock is frozen magma, right? Is there a fundamental difference?
Marion?
No, there isn't. Let's just step back a bit and talk about Pluto for a minute. These messages that are coming pixel by pixel over the last year or so. So Pluto is extremely cold. Its surface is about minus 200 degrees centigrade. So what's the surface of Pluto got on it? Well, it's ice, essentially. There's water ice, which is a fairly rigid, it's like the bedrock of Pluto is water ice. And then there are some ices that move around a lot. There's nitrogen ice and there's carbon monoxide ice. And they're moving around, they're sublimating, and then they're condensing somewhere else. And the reason I'm telling you all of this is because if you look at the topography on Pluto, there are mountains and ridges and bumps and lumps. And if they're old, they've got craters on them, that's how we know they're old, they must be made of bedrock. There are these two mounds which they found. They're not mountain ranges, they're just isolated circular mounds, and they're about 150 kilometres across and they're about 6 kilometres high. Now, that's a pretty big mound. We've got some things vaguely similar to that, like Hawaii on Earth, the biggest volcano on Earth. Anyway, there are these things. Because they're really big, they must be made of something strong, so they're probably made of water ice. And they've got a central depression in the middle. They look just like a volcano, a really big hole in the middle, which is what a volcano looks like. And their surface is not got many craters on it, so they're quite young, but it's got a very curious sort of hummocky texture. And that's essentially all we know. It's just pure speculation. We're just saying the shape of these things looks like a volcano, but we don't know any more than that. It's very exciting science.
We're taught at school about blue and brown eyes, and I clearly remember asking the teacher, what about green eyes? And was told not to worry as it wouldn't be on the exam.
In this month's Naked Genetics podcast, we're finding out whether the public is really ready to look inside its genes and how superheroes might help. Plus, a lab for everyone and a gene of the month that's crunchy on the outside. Listen and download now at nakedscientist.com/genetics. This is The Naked Scientists with me, Kat Arney.
And also with me, Chris Smith. And it's Q&A time this week. So if you would like us to answer your science questions, then ping us an email. It's chris@thenakedscientist.com, and we will do our best to include them in our next Q&A show.
Chris, here's one for you. We've got a question from Safia who says, I have 5 girls. Wow. For 15 years I've wanted to have a boy. She changed her diet, used an ovulation kit and so, but they did not work. Can you explain why she has not conceived a boy? This is a tough one, I think.
Well, it's actually her husband's job, isn't it? Because as geneticists will tell you, there are sperms that have X and there are sperms that have Y. And if you are having a girl, then your egg has been fertilised by a sperm that has an X chromosome in it. If you are having a boy, then your egg is being fertilised by a sperm that's got a Y chromosome in it.
Because women's eggs just have one X chromosome. All eggs have an X chromosome.
That's right. Women are just XX. That's their genetic makeup, whereas men are XY. Therefore, the only genetic material a woman can contribute to her egg is an X chromosome, whereas men can make sperm that have either an X or a Y. Now, why should you only have girls? Well, what's the chance of having a girl? Well, you've got roughly a 50-50 chance, because there's equal numbers roughly of X and Y sperm in a healthy person. So what's the chance of having 5 in a row? Well, that's 1/2, a half, to the power of 5. So that's a half times a half times a half times a half times a half. And that means you've got 1 in 2 times 1 in 2, which is 1 in 4, times 1 in 2 is 1 in 8, times 2 again is 1 in 16, times 2 again, 1 in 32. It's about a 3% chance that that's happening. But that's not zero. And so therefore, just because it's low odds doesn't mean it is abnormal. So I would say that somebody has to be that 3%, because we believe that the population is what we call a normal distribution. So it's probably perfectly natural. There's probably nothing that this lady can do to shift the odds, apart from to go and see a clinic who can put the sperm through a system to sort out the X and the Ys, which you can do. Some people don't agree with it. They don't think it's ethical. It may also have health problems. Who knows what the long-term consequence of doing this is, and thwarting nature in that way. But the bottom line is, you should be, as one person put it to us, delighted you've got 5 girls, because they're much easier to bring up than the male equivalent, because they said the conversation extends beyond unless of course you do happen to like all the mates around from the pub for beery parties and shirts and stuff strewn all over the dining room.
I think girls smell nicer as well.
Got a question here for you, Andrew. Very cute this. Pia says, my daughter recently turned 10 and we started talking about planets rotating around the sun. We were wondering whether you end up in exactly the same spot in the universe on your birthday because the Earth goes around the sun in 365 days. So does that mean each year on your birthday you would be in the same spot with respect to the sun? Or is that position constantly changing?
Well, that's a really good question. Yeah, you're absolutely right. In 1 year, the Earth will return to the same spot with respect to the sun. But the sun is moving through space, and the sun is moving, dragging all the rest of the planets and the solar system with it. The sun is moving with respect to the nearby stars. All those nearby stars, including the sun, are in turn rotating round the galaxy, our galaxy, the Milky Way. Our galaxy, the Milky Way, is also moving through space with respect to the other galaxies in our local group of galaxies. That local group of galaxies, including the Andromeda Galaxy, is moving through space with respect to the Virgo supercluster of galaxies, of which we're part. And that Virgo supercluster of galaxies is itself moving through space with respect to the cosmic microwave background, the background glow of the Big Bang, which we can imagine as a sort of static reference against which everything else moves. So everything is moving. Yes.
Also, that's assuming that it's exactly 365 days to go around the sun, but it's not, is it?
It's not. It's about 365 and a quarter days, which is why we get that extra day every leap year, every 4 years. So, yeah, there's a little bit of adjustment due to that as well. But with everything else going on, it's a lot of
Who cares? A quarter day here and there, February 29th.
So relative to the sun, you are in the same spot on your birthday, but relative to everywhere else in the universe, you're not.
After 365 and a quarter days, you're relative to the same spot with the sun. But yeah, it's complicated.
So let's have one for you, Laura. Patrick wants to know, what does each part of the brain do to help keep us alive? What's going on?
Goodness me, this is a huge question.
It's basically like all of neuroscience, right?
Yeah, absolutely. I can do that in 3-4 minutes?
Yeah,
Easy.
yeah.
So maybe I should just take you through a bit of a whistle-stop tour of the brain. If we have our brainstem, and that takes care of things that we don't think about.
So what's that? That's the bit at the back of my neck.
Exactly, the bit where you can feel like...
Let's do this at home, everyone. Okay, feel the back of your neck.
Yeah, let's take you through. So everyone feel the very bit where you can feel it's a little bit bony, a little bit of protruding. That's where you have your brainstem, and that's where it controls things like swallowing, breathing, and all the things that we don't think about.
This is the really old bit, isn't it? This is like the ancient brain.
It absolutely is, and for very good reason. Otherwise, we wouldn't be able to breathe or function. And on the back of there's also something that you can't feel, unfortunately. But if we move just our hand a little bit further up, we're on the cerebellum. And the cerebellum is well known to most people on a weekend because it's the part that controls our movement and our gait. And it's the bit that alcohol allows us to be a little bit woozy. And so we can't walk straight. And then
controls our dancing, to put it a bit more positively.
Blame it on the cerebellum, absolutely. Yeah. And then we have the cerebrum, which is really where we're coming up into the hemispheres.
So this is the top, like the big bits at the front of the brain, the big stuff, the grey matter.
Absolutely. So this is whenever you see a picture of the brain and you see it kind of looks all folded. And so those are called the sulci and the gyri. And the reason that they're like that is because you need more surface area to fit in the 100 billion neurons that we have that allow us to talk, walk, and for you to listen to me now. If you pop your hand on the back of your head again, you've got it resting over the occipital lobe. And this is where the visual processing is done. So we're looking...
So seeing at the back of the head.
Absolutely. Light, movement, colour, so on and so forth. And then if we carry on moving forward, so as if we're going to come to the front of our forehead, but stop before we get there.
So this is where our headphones are resting.
Absolutely. So if you've got them at home. And then we're at the parietal lobe, which is kind of responsible for visuospatial information and sensory integration because our sensory cortex sits in there.
So that's putting everything together from the world around us.
Absolutely. So when we were talking earlier about feeling up on our bottom, the seat, things like that. And then if we carry on walking forward, we have the frontal lobes. And this, as I mentioned earlier, is relating to our personality, our executive planning skills, our working memory, so on and so forth. And then we also have, if you were going to decide you didn't want to listen to me anymore, so you wanted to put your hands over your ears, you'd be very close to the temporal lobe. And the temporal lobe is responsible for hearing, as you would imagine, and also for memory functions. So that's kind of a very quick tour. But if we think about how the hemispheres may differ, because what we're increasingly finding is the brain is very networked, and it utilises both hemispheres for many of the functions that we carry out. But there is some form of lateralisation in some of the things that we do.
Because I think I covered this recently. We did the myth busting on the, are you left brain or right brain?
Yes.
But there are some things that are left and right, aren't there?
Absolutely, yes. So mainly, and the one that most people have heard of is language lateralisation, and that in most right-handed people is taking place within the left hemisphere. Very interestingly, there is a subset of left-handed people that it will actually be right hemisphere localised, not all, but some, and fewer still, some people that there's bilateral organisation, so that's very interesting. And in terms of the right hemisphere, we find from looking at brain injury, most notably this hemispatial neglect, which is really interesting, where you can still see things in one side of visual space, but you just lose the ability to attend to it. And that seems to be more long-lasting if you have damage to your right hemisphere than your left, meaning that it's likely to be more important in visuospatial processing.
So I think basically the summary is all bits of our brain are really important,
yes,
and they're all used, but they're sort of different areas that are special.
Yes.
Thanks very much.
Now, Marion, got this question here from Devin, who says, how do volcanoes affect global warming? Are they a big contributor?
That's a really interesting question. Now, volcanoes are part of why the Earth stays the same temperature or the same climate for long periods of time. It's all part of the carbon cycle. So inside the Earth, there is a lot of carbon dioxide, and it comes out when volcanoes erupt, or sometimes continuously coming out of degassing magma underneath volcanoes. So there's a continuous stream of carbon dioxide coming into the atmosphere from the centre of the Earth. This is primordial CO2 that was there when the planet was made. Now, if that carried on, then clearly we would just have a carbon dioxide climate, and that's not actually true. Carbon dioxide is quite rare in the Earth's atmosphere, and that's because there is a carbon sink, which is to do with weathering. So when you get CO2 in the atmosphere, it dissolves into rainwater, dissolves into river water, and turns into carbonic acid, and that weathers the rock, and then eventually you end up by making limestones. So all that carbonic acid goes into the oceans and then reacts with dissolved calcium and makes calcium carbonate, which turns into either animal shells or into limestones, which then trap the carbon dioxide. You know, it's now in rock and it's no longer in the atmosphere.
So there's a sort of equilibrium going on with the volcanoes are returning to the atmosphere this stuff, and there are processes drawing it down. So we end up with the levels we've roughly got.
We have a balance, and it just balances itself. So if we have a period of continental collision, for example, and you're making all these mountain belts, you've suddenly got loads and loads of rock that's available for weathering. So you'll have a momentary period where you're drawing down a lot of carbon dioxide from the atmosphere. The Earth cools a little bit, but because the Earth's cooled, all those reactions that can then turn the dissolved carbonic acid into rock slow down. So the whole thing can get back into balance.
And that's why we see what ice age is coming in geological timescales, because you get these processes happening, like India migrating down from where the Antarctic is up to crash into Asia and make the Himalayas. This exposes lots of the seafloor of the Indian Ocean and pulls down CO2, and we get an ice age.
Well, yes. You've made that big batch of nice fresh rock that's all ready to be weathered. And it doesn't make ice ages, though. I mean, the ice ages are cyclic, to do with the way the Earth is precessing around the sun and the tilt of the Earth's axis. But that's not really my field at all. But one example I'd like to give, actually, is what happened 252 million years ago, when there was an enormous outburst of volcanic activity in Siberia. It's the Siberian traps, they're called. Just masses and masses and masses of basalt poured out onto the surface of the Earth, pumping carbon dioxide into the atmosphere. And it actually warmed the Earth up so much, it got hotter by 8 degrees, which, when you think we're trying to limit what we're doing now to 2 degrees, is an enormous, enormous heating of the Earth. And it wiped out 97% of the species on the planet, this global warming event, because the carbon dioxide was pumping into the atmosphere so fast that the normal sort of drawdown procedures just got completely swamped. So it was a sort of massive version of what we're actually doing now.
I hope it doesn't go that far. Now, we saved the hard questions right for the end. Andrew, quick one for you.
Could you simplify gravity for me? My problem is, if the International Space Station has microgravity only 400 kilometers above Earth, how does the sun have an effect on us and on the other farther away planets when it loses its effect so quickly?
Andrew?
Right. Well, the thing is, on the space station, people talk about zero gravity, but of course it's not. The gravity is there just as it is everywhere else around the solar system. It's better to think of being on the space station as being in free fall. Now, if you were to, let's say, be in a lift and someone carelessly cut the lift cable so that the lift plummeted down to the Earth, whilst you were falling, you would be in free fall and you would feel weightless. Because when we say you have weight, what we mean by weight is the force pushing up from the Earth into your feet. So if you're standing on the Earth, the weight that you feel is gravity is pulling your body down, but the Earth is, if you like, pushing you up. There's a reaction force, a contact force pushing up through your feet, and that's what we experience as weight. Now, if you're in the space station, going around the Earth in orbit, you've still got the force of gravity pulling you down. In fact, that's what's holding the space station in orbit. The space station, if you like, is constantly falling, but it's moving sideways, so it's falling round the Earth, and that's what the orbit is. So the space station is going round and round the Earth, constantly falling. The astronaut is continuously in free fall, and so they're not experiencing weight, but they are experiencing gravity.
Isaac Newton had a beautiful way of getting his head around this, which he wrote up in his Principia. And his point was, if I had a gun and I fired it quite hard, the bullet would come out and under the influence of gravity eventually drop to Earth. If I fired it harder, the bullet would go further before it dropped to Earth. If I fire it really hard, then the bullet will actually keep dropping towards the Earth. But because the planet's curved, the curve of the planet falls away beneath the bullet, so the bullet never touches the ground, and you are in what we call an orbit.
Exactly
And so the bullet is not weightless. It's feeling gravity pulling it down, but it's always falling towards the Earth and missing.
And just the same with Tim Peake.
Absolutely, and he got home safely, which is great. Kat, can you wrap this one up for us? Ruby wants to know, why do countries with similar standards of living have different rates of cancer?
Wow, I've got like 2 minutes to do this. It's also, cancer is not just one disease. There are many different types of cancer. So there are different rates and different causes of cancers in different countries. Actually, it's really hard to know exactly what sorts of cancers happen in different countries and the rates, because not all countries keep really good cancer statistics. In the UK, we have some of the best cancer statistics in the world about the different types of cancer we have. But broadly, we can see there are differences. So, for example, in China, in Asia, there's lower rates of certain types of cancers. In the West, in America, in Europe, we have high rates of things like breast cancer and bowel cancer. In Africa, there tend to be higher rates of things like cervical cancer and cancers linked to infectious diseases. It's a very complex global picture. So it's better to kind of pick one type of cancer and look at it. But we do know there's a role for genetics. So, for example, people of Ashkenazi Jewish heritage are particularly more likely to have certain types of inherited risk of cancer. And diet also plays a role as well. So we do know that
so you've got a combination of the genes you're born with, the environment you live in,
your nature and your nurture, and
they unite.
you know, and how you go on through life as well.
Kat, thank you very much. And that is it for this week. Thank you to our wonderful guests, including Andrew Norton, Laura Ford and Marion Holness. The producer was Greer Jackson. Next week, we'll be travelling off to the suburbs to uncover just how ecologically diverse they are and why we should be protecting these brownfield sites over green belts. The Naked Scientist comes to you from Cambridge University, and it's supported by the STFC, the EPSRC and Rolls-Royce. Thank you for listening, and until next time, from us at The Naked Scientist, goodbye.